In this example, we have the same idea with the previous table, but let's say make it more compact because if there are 20, yeah, it will be more compact to calculate the numbers. Okay. So let's see with different example, and we are going to look at the rank score, leaf index, and DCG, IDCG, and NDCG. Okay. So the rank score here, as you know, we have 5 recommended items. And from those 5, the user hit number 2, hit number 3, and hit number 4. Okay. Then using the rank score, we can use this formula. So let's suppose, okay, there are 5 recommended items with 3 which are relevant, or 3 hits. And we have the ranking half-life, or the alpha is, let's make it 5 multiplied by 0.5 equals to 2.5. But maybe for easy calculation, let's round it to 2. Okay. And we have 1 divided by 2 power of 2 minus 1 divided by 2. 2, this one, it means this is the rank number 2. This is the rank number 3. And this is the rank number 4. Okay. So we get the rank score is 1.56. What about the maximum? The maximum means that we are going to look at the position 1, 2, and 3. The position 1, it is rank number 1, the position number 2, and the position number 3. So the result is 2.21. The rank score, it means the normalized values. We have the rank score P, which is this one, 1.56 divided by the rank score maximum, which is 2.21. And the rank score is approximately like 0.71. So in this case, yeah, the rank score is close to 1. It's quite good. Okay. It's higher than 0.7. It's close to 1. So the recommendation item is quite good. What about the leaf index? Okay. When we use decile, what is decile? We want to make into 10 groups, but we have only 5. Then how can we divide this one? The idea is still the same. We want to make it 10. If we make as 10 groups, so the S1 will be multiplied with 0.9. The S2 will be multiplied with 0.8, and so on. Because we have only 5, then we can divide the weight into 5. It means if it is in the first, let's multiply with 1. If it is in the second, let's multiply with 0.8. If it is in the third, let's multiply with 0.6. If it is in this fourth rank, let's multiply with 0.4. If it is in the fifth, let's multiply with 0.2. Okay. Then we can get the leaf index is 0.8 multiplied by 1 because it is available in the rank number 2. 0.6 multiplied by 1, it is available in the rank number 3. And 0.4 multiplied by 1, it is available in the rank number 4. Then we will get the leaf index is 0.6. We have 3 items. Okay, we have 3 items. So we divide with 3, then the result is 0.6 for the leaf index. What about the DCG, discounted cumulative gain? Based on the formula, okay, the idea is similar with the rank score. We want to know what is the rank of that product which has been recommended and it is relevant to the users. So among those 5, we can see that the hit product is located in the position 2, position 3, and position 4. Okay. So we just use this formula, CDCG. So we can get the value 2.13. So if you look at the formula again, this is the relevance of the recommendation at position I. Of course, if it is in the position 1, we have the relevant 1. So we want to know the relevant in the position I log base 2 of I. So if it is in the position 2, then yeah, we have to. If it is in the position 3, we put 3. So the idealized discounted cumulative gain means this is the position similar to the maximum. What is the maximum? If it is located in the first, of course, this is the maximum. If we have 3 items, then we want to know that the product is located in the position 1, 2, and 3. That's why in the example, the hit is located in the position 2, 3, and 4. The ideal or the maximum, we want to know if it is located in the position 1, 2, and 3. Okay, because we have 3 items. And the formula is using the log. We got the DCG is 5. DCG 5, which means for the 5 recommended items, the value is 2.13, and the idealized the maximum of 5 items is 2.63. The normalized DCG, the normalized discounted cumulative gain, means the discounted cumulative gain, this is 2.13 divided by the idealized. So we get the value 0.81. So this is similar with the value in the rank score. How to interpret it? If it is near by 1, then the rank of those items are the same or nearby the recommended model. If it is very low, let's say nearby 0, then the hit ratio is very low, or the hit happens in the lower rank. That's meaning about this DCG, IDCG, and NDCG. Now, this is just an experiment. How if we reduce the ranking half-life, or how if we reduce the alpha? The previous one, alpha, is like the number of recommended items multiplied by 0.5. So if it is 5 multiplied by 0.5, it is 2.5, and we make it equivalent to 2 for easy calculation. Now, let's suppose we want to reduce it to 1. What happened? When we reduce to 1, so the value is a little bit higher compared to, the value will be lower compared to this one. And this rank score maximum is also lower. This one using the ranking half-life equals to 2. This one using the ranking half-life equals to 1. So the rank score, we got the value is 0.5. Meanwhile, using the previous formula, we got the value 0.71. So the half-life, the ranking half-life will affect the result. That's why when we say this is the ranking half-life, yeah, it will be better to keep the value maybe in 50% of the recommended items. If you make it lower, like this one, 2.5 actually, but you make it 2. So let's suppose we make it 1. Then you can see the value is different. If you look at the result, okay, somehow the result will be like this. The rank score, the value of rank score will be lower than the leaf score. So the rank score, we call it, this is the exponential reduction. For the leaf score, it is only the linear reduction. And the NDCG, we call it, this is the log reduction. Can you understand? In the formula for the rank score, we have the exponential reduction. This is the exponential reduction. 2 power of n. So this is the exponential distribution. Okay. And then the leaf index, we just use the linear reduction. Linear. The first is 1, and then 0.8, and then 0.6, and then 0.4, 0.2. So linear. But the NDCG, IDCG, and DCG, it used the log function. Log of this one, log of this one, log of this one. Okay. We can also, again, do this one with the average precision. With the average precision means I want to know the rank precision matrix that place emphasis on the highly ranked correct prediction or hits. So it is essentially that the average of precision values determined after its successful prediction. So you already know the average precision. This is the rank. And then we have the hit on the position 2, 3, and 4. And I know with the average precision, we have 3 items. So among 3, yeah, so this is, 1 divided by m. If you still remember the previous formula using the average precision, 1 divided by m, we have 3 products. So we have 3. And then in this 3 position, yeah, you can measure. This is in the second. Okay, in the second means we have the first is 0. In the position second means out of 2 products, one has been hit. In the third position, among 3 products, okay, so 1, 2, 3, 2 has been hit. In fourth, among 4 products, 3 has been hit. And the last one, 5, among 5 products, 3 has been hit. Okay. So in order to make the average precision, because item 1 and item 5 has not hit it by the user, so we have only 1 divided by 3 multiplied by 1 divided by 2, 2 divided by 3, and 3 divided by 4. So this is the average precision of this data. What about this data? We have, this is position 1. So again, we have the precision. The position 1 is 1 divided by 1. Among 1 item, 1 has been liked or has been hit. What about the second? Among 2 items, 1 has been hit. What about in the third one? Among the third item, 1 has been hit. What about this one? Among 4 items, 2 has been hit. And this one? Among 5 items, 3 has been hit. Okay. So we can calculate 1 divided by 3 because there are 3 items that has been recommended. And the average precision is in the position 1, which is 1 divided by 1. In the position 4, which is 2 divided by 4. And then in the position 5, 3 divided by 5. Then we can get the average precision is 0.7. Okay. Yep, the remaining is only about the analysis. We have a dilemma. The dilemma of establishing ground truth. It means the ground truth, yeah, what is the problem with the ground truth? So IR measures, IR is the information retrieval. IR is the information retrieval. IR methods are frequently applied. However, in the offline experimentation, we can use rating. We can use the transaction. And when you use the online experimentation, yeah, we have rating and we have like feedback from the users. We can have the historic session. Historic session means not all recommended items are rated. Okay, so we recommend items, but no rating. That's all. Your question people. How can we know the rank? If we have 20 items, the rank, this is from which file? So this dilemma. If we use just historic session, okay, yeah, we can just assume. So sometimes in the online e-commerce or the movie something, they have assumption. They use their assumption. Because not all recommended items are rated, especially if you have new movie. How can you recommend new movie when there is no rating? So yeah, we just use randomly or they have some rules. or live interaction. All recommended items are rated. So for example, now you know about live streaming. Okay? The live streaming, you can see a lot of comments and directly they have the rating. Okay? So in that case, it's the live interaction. Rating of unrated items known but interpreted as bad. So that may happen. We have no rating, but in the algorithms, it mentioned that it is not recommended items. Good or bad ratings of not recommended items are unknown. So if it is in the online, we cannot get the idea whether it is good or bad. Because if you look at the live streaming, you can get a lot of comments directly, but it is difficult to directly know whether the user like it or not. We may just know the user purchase it or not. So if the default assumption does not hold, then yeah, we may have like this one. True positive may be too small, false negative may be too small. And for the online experimentation, we have the false true negative that cannot be determined. And as the result of this offline experimentation, the precision may increase. The recall may vary. In this online experimentation, the precision is okay, but the recall is questionable. So results from offline experimentation have limited predictive power for online user behavior. So that's why when we do the recommendation system, I hope that you can try to practice with the existing code. Maybe the result of your model is good, but the predictive power may not be good. Okay? The model is good, but the predictive power maybe is less than the online user behavior. So some on offline experimentation, the Netflix competition. Okay, I think I will not discuss in detail, but the Netflix competition, they use the history data and they attempt to get the improvement of the RMSE. So they want to improve the error. What is the best way to improve the error? And they mentioned that the error should be comparable with other kind of system. For example, how big is the improvement? Yeah, the historical data, there are 480,000 users and 18,000 movies and 100 million ratings. And yeah, they need to separate the probe set. The probe set means the set of data that has been used for the competition for teams evaluation and the quiz set. So they have the leaderboard. It means if someone can achieve better, then yeah, they will be in the number one in the leaderboard. The test set is used by Netflix to determine who is the winner, who get the best RMSE. So they usually have this kind of different set. Maybe we know only the training set and the testing set, but actually in the fact, there might be different set like this one. Yeah, when we do with this kind of performance metric, we may have also some observation. Whether we can also look at the statistically significance. Are observed differences statistically meaningful or due to chances? So if you want to do with the statistical significance, we can look at the ANOVA. So I do not explain ANOVA in this case. Or you can use any statistical analysis with the null hypothesis, it's 0, and the alternate hypothesis. So if the matrix deviate, deviate, metric 1 and metric 2, yeah, you can also look at the metric 1 and metric 2. If it is the deviation is high, okay, then maybe it is not robust or something with different experiment, okay. Or the practical importance of differences, the size of the effect and its practical impact. Or we can also look at the external validity or generalizability of the observed effects. So it means if I know the user 1, he liked the movie number 1. So we need to check what is movie 1. Okay, movie 1 is Toy Story. Okay, if movie 1 is Toy Story, if we recommend movie 2, movie 2 is Toy Story number 2. Okay, then it means it is the same. So we need to check the practical importance of the result. So for the online experimentation, there are also some kind of works. Let's say in the, maybe this is very old works. Okay. It is based on the online games or cell phone games. And when they download the games, they give rating. So this is just an example. And yeah, the ratings can be also in different ways. So this is the work from one paper. Maybe I will not discuss in detail because it is only one paper. And the rating, the interesting point is this one. They do not use the rating from 1 until 5, but they use rating from -2 until 2. So if it is negative, then it is not that good. If it is positive, then it is good. So this is something that we can consider also for the experiment design. And the hypothesis, yeah, can be in different way. Whether we want to make personalized or non-personalized recommendation. Personalized means specific to users or some categories. Users who are students, users who are older, users who are male, users who are female. So we can say that is personalized. If it is non-personalized, then we just recommend to any users. Of course, there will be some effect. So the result, it increased the conversion rate and it is stimulate the additional purchases. Okay, so for the remaining, I think it is just only a case study and how the works do with the experimental results. Okay. This is just also experiment based on the previous works, how they apply the metrics and how the recommendation system by each month. So they try to measure by each month. After July, after they give recommendation, what is the effect on July? After they give recommendation, what is the effect on September? After they give recommendation, what is the effect on October? And so on. So they measure monthly. So the most important thing is how to interpret the result. So if the result is good, it means it is not like random assignment. Random assignment. So we can randomly assign. Okay, do you like this movie? So in the decision, we do not want to have recommend like random. So we want to know that the recommender system will convert the users. So does the recommender system itself cause users to convert? If the users do not change, then the recommender system is not good. So that's the practical effect. And some hidden exogenous variable might influence the choice of RS. For example, maybe there is an economic reason, or maybe there is a internet speed reason, and other things that we cannot measure it. So there's also another effect on the other domain. Maybe in the movie it is different with tourism. If it is related to electronic products, it's also different. Okay. Yep. The other thing is about what is the most popular data set for the assignment we can use for movie. Next is come and there's this platform platform. And the most popular is Christian and the pop. And also you can use MBD and comments. So we already learned the tools today. And yeah, until mid-exam, you will see some of those questions. And if you look at the journals later for the assignment 2, you will see a lot of precision, BCG, rank score, and all the metrics. And especially if you read the good journals. Okay. Okay, I think that's all. So you learn about the general principle about how we can measure the recommendation techniques. Okay. And yeah, the remaining part I think is not that important as long as you understand all this precision recall, MAE, RMSE, and the possible metrics for the recommendation system. Okay, I will stop.